Okay, let's go back to the material. So actually the model is quite simple. Multiplication of with your transmission function. If you use raised cosine approximation, you have two exponential terms, and they can be combined with your carrier frequency term together. When that happens, actually you can see more coupling occurs. Okay. Now you see omega n plus 1 and omega n minus 1, the mode frequency of two side modes. Okay. So if you observe the first term on the right-hand side, which is here, okay, there is no coupling because the left-hand side is omega n, right-hand side is also omega n. So it means the nth pulse mode contributes to itself by a negative term minus delta m times En. So the negative sign means a loss effect, okay, in one round trip time, big T, which is natural because you are using modulator, intensity modulator. You will lose some energy anyway. And the first term simply describes the energy loss due to the modulator, but there is no coupling. Okay. If you observe the second term on the right-hand side, which is here, mathematically it's modeled by this way. En plus 1 or minus 1 prime, physically it means the phasor of two side modes, right? The new phasor of the two side modes is approximated by a positive number, delta m over 2 times En, the phasor, the old phasor of the nth pulse mode. Okay. So together, the nth pulse mode contributes to its two neighboring modes by a positive term or a gain term in one round trip. Okay, so it's different from the first term. The first term means the nth mode contributes to itself by a loss due to the intensity modulator. But the second term means the nth pulse mode contributes to not itself, but its two neighbors by a positive term, which is a gain effect, not loss effect, right? Due to the intensity modulator. Although it looks controversial, why a modulator contributes to gain, it seems controversial, but it's only the gain to the side modes, not to itself. Okay. But mathematically, we will take a different way to write, to formulate. The original one is this one. And after the interpretation, we got this. Or you can take a different interpretation. The n plus 1 or minus 1's modes, the two neighboring modes, contribute to the central mode, the nth mode, by the gain effect in one round trip. It's equally the same, right? 好，我用中文解释好了啊。原来是这样，那你看公式解读出来的意思就是什么？第 n 个 mode 在中间，因为 modulator 贡献的能量到左右两边，对不对？可是换句话说，也可以怎么讲？左右两边的 mode 因为 modulator 贡献到中间的 mode 一样嘛？啊，那但是数学的写法就要换成这样 ，right？ En prime means the new phasor of the nth pulse mode is approximated by a positive number times En plus 1 and En minus 1, the two old neighboring modes phasors. And the gain effect contributes to the new phasor of the central mode. And we will use this one in the modeling. instead of the original one. But you can justify why can you do so by these interpretations. Is it okay?
旁边的两个墨只贡献掉它 n 倍的 n 给 en 加1跟 en 减各贡献掉它 n 倍的 en 给1。
对啊，我可以把中心移动，你就可以了解嘛。
那为什么就是这现在的 en 号它没有它自己中心墨的
有，我还没有全部写完，这只是写 Simon 对他的贡献而已。对啊，他还有一项就是自己对自己的贡献，合起来才是全部。So this is the combination. The contribution to itself, it's a loss effect. Contribution from the neighbors is a gain effect. Combining them together, you got the total equation like this. Okay, this is your answer to your question. And rewrite this one by dividing big T, the round trip time, you got this. And now you are experienced. Why do we need to do so? Because we want to transform a difference equation into a differential equation, right? So this is the result. The rate equation 2 prime now is modified by adding a term which is here, okay, to the right-hand side of the equality. Just like what we did when we including the contribution from the gain median, right? You got one term, add it to the right-hand side, you got a new equation. This time we do the same thing. Formulation shows contribution from the modulator is represented by these terms. So you just add this term to the right-hand side of equation 2 prime. You got the updated equation, rate equation. Now it's deal with all the effects, the cavity, the gain median, and the modulator. Okay? And if you take difference quotient with big T approaches 0, right? You can transform from difference equation to differential equation. And this is the corresponding differential equation including every effect. Okay? Looks complicated, but at least now you can clearly identify the mode coupling occurs because n-1 and n+1 appears together in one differential equation. So that means you cannot solve En independently. You need to solve a system of equations, actually infinitely many differential equations together. Then you are expected to solve E sub n, n from 0, 1, plus minus 1, plus minus 2, all the way to the infinity. A lot of unknown functions to be solved. Okay. Now, before we looking for the solution, at least we can answer how are the modes are phase locked. Why are these phasors referred to more lock lasers? What happens such that you can have more locking? Okay, if you observe the equation, say the red arrows represent the pulse modes, and the green curve represents your spectrum. If you pick up one specific mode, the nth mode as an example, say En, when you have a loss modulator, and the loss for the mode itself means a downward arrow represents the loss. Okay, so due to the intensity modulator, the mode itself contributes to a loss. So you have a downward arrow. But the second term means the central mode, due to the loss modulator, contributes to gain, so upward arrows, to the two neighboring modes. So in this picture, it means the energy can be transferred from here to the neighboring modes. If energy are coupled together, their phase are coupled together. Just imagine what does this mean? Each mode means a sinusoidal function, right? So when this sinusoid oscillate upward and its energy transferred to its two neighboring modes, it means there is a force to push the two neighboring modes oscillate upward together, right? So in the presence of energy transfer, eventually all these modes will oscillate together, just like hand-to-hand shaking. 没有耦合就是各自震荡，不会锁膜的，所有的 phase 都是乱的。现在你有能量的转移，所以当我的能量是我在做往上的震动的时候，我能量送出去，当然会把两侧的 mode 也拉上去嘛，跟着我一起动。那这个 coupling 不是只有这里到这两边啊，还会继续下去，这里又会到这两边，这里又会到这两边。So eventually all the modes will oscillate together. Then you have phase locking, in phase. Okay? So that is the answer to why all these modes can oscillate in phase. Because of energy transfer mechanism due to the loss modulator. Okay. Okay, so far we just model the yes.
刚刚那你要怎么，就是它这样一起震荡的话，你要那我可以说它其实都是 auto phase， 还是你要怎么说它的
in phase 的意思是，比如说大家都是0度，就是大家都是 cosine。
可是一个减少，另外一个会增加，那这样
一个减少，一个增加，什么意思？
就是那个中心的时候，它是减少把能量分给旁边的。
对对。
那这样。
就是某一个 cosine 它牺牲一点 energy， 但是 energy 没有凭空消失，它是传给了也有一些消失掉的啦，就是自己的 mode 会变弱一点嘛，我的 cosine 变低一点，振幅低一点，但是我会把一部分能量贡献给两侧，这两侧要是没有 modulator， 最后根本就是死掉了就像 CW laser 一样，什么都没有。现在因为你把能量搬给它了，传给它，所以它还可以震，而且会跟你一起震。所以它的 picture 是这样子，不但达成 more locking 锁膜，而且呢，靠着这个能量的搬动，才使得这些 modes 虽然它的 loss 超过它直接看到的 gain， 它还能活得下来。所以 maybe 我可以给你看这个 picture。You see this mode. The gain could be here, but loss is so high, without energy transfer, it will die off. But with energy transfer from here, it can survive. Okay, so remember this level is your cavity loss. Okay, the green one is your gain spectrum in steady state. In principle, they will die off, but because of energy transfer, they survive. That's why you can have short pulse. And not only these modes, side modes survive, but also phase locked. Okay, is it okay? Thanks for your question.
现在这样这个分布它会变得更平，因为你中间分比较多能量给旁边，跟你旁边的能量回来会比较少。
搬的比例可能都是叫做 delta m over 2, which is a constant for any m, for any mode. But the real magnitude depends on the mode energy itself. So you are right. This mode only contributes to smaller amount of energy to its two neighbors compared with this one. The ratio is fixed, but this term is smaller for side modes. 所以最主要的能量 贡献是这一个没错，它的 EN 最大。
所以那2个紫色箭头应该右边那个比较大一点，这样。
这个哦，画图你说这个长短不一，是不是？
就是右边那个是不是会比较大一点？右边那个还是一样？
我画这个箭头只是说，这个对它的贡献跟这个对它的贡献是一样的，这不代表这个是它的高度，没有，我不是在说这件事。它搬到左边右边的贡献是一样的。对对对对，全部来自它，那有损失也有增加。
所以中间会拿到右边来的比较多，左边来的比较少。
roughly yes。
所以说这个模型最后会震荡到每一个，它可能就是震荡到变成每一个都一样高。
不会，就是它没有办法让你的 spectrum 最后变成一个 square function， 没有办法。
它名称就是因为最中间那根距离，我
如果你
没想到就
对，右边的2个给中间的那个比损失还要少，然后它可能掉出 gain 的话，它就会往下，它什么时候它中间会带到的。可是因为你旁边又你旁边现在变高了，你又再给回它又会涨上去了。所以就是你要达到最后的那个 dynamic stable 的话，它应该是要最后的每个都大家都是平的，它这样才不会给。
那你有考虑你的 gain spectrum 不是平的吗？就是绿色的就是 steady state gain spectrum， 每一个 frequency mode 看到的 gain 是不一样的。就是我最后的能量也其实不完全靠它搬嘛，还有我自己看到的 gain， 他看到 gain 很小，他看到的 gain 比较大，已经很接近 loss， 它这个离 loss 还有很远，这也会影响到最后的能量。
只是如果你照那个 Carbon equation 的话，它是 EN 的 EN plot 等于 EN 乘以减掉它 n， 就是说中间的小调它直接掉它 n 乘上 EN， 然后旁边的小调它们各自的1/2乘上掉它 n。如果它不一样，它表示是那个 EN plot 它会一直改变。
But this model only takes the modulator effect into account, right? Here. You have gain term, you have cavity terms. Right. 哎，你不能只看这几项，只是讲一部分，只讲这里而已。Okay. So the next step is, what is the solution? But dynamic solution is pretty difficult, pretty complicated. So we focus on steady state solution. So let's rewrite the red equation we just derived. It can be simplified if, first, only steady state is of interest. Second, modulation period matches the hard cavity round trip time. So if you are only interested in steady state, the first term can be dropped. Time derivative is 0. That is steady state. And secondly, if your modulation period, although is different from your cold cavity period, but if it is the same as hard cavity increment period, the second term can be dropped. Okay? So now you can understand why the detuning factor delta is non-zero, purposely non-zero. Because we need a non-zero delta such that this term can be really 0. But the physical meaning is quite easy. You have your modulation frequency has to match the hard cavity instead of the cold cavity. Because the true repetition rate or repetition period depends on the hard cavity condition, including the gain median introduced delay increment, right? 所以为了这个原因，所以其实你要这件事就是在讲 ，you have to do synchronization. Your modulation frequency have to be carefully controlled, perfectly match your cavity. Then you can achieve more locking. Otherwise, this term will not disappear. Okay. But for simplicity, we assume we can do so. You can use feedback cavity or feedback driving frequency technique to do so, to achieve this condition. In that way, the first two terms can be dropped. So then you have this, okay? And the rearrangement, you got this. Okay. But if you feel it's still unclear for you, you can rewrite it as a matrix form, which is like this. This is the unknown vector to be solved. The phasors of different modes. These are the unknowns you want to solve, right? And this is the matrix where you only need to know delta M and L, the modulation depths and the cavity loss, which are two parameters you should be able to get in advance. So this is a known matrix, okay? This is an unknown vector. And the right-hand side of equality is small g. What is small g? The gain coefficient, saturated gain coefficient according to lesson 1, right? But you know, this is not a given number. This is an unknown number as well, right? Just like in CW laser analysis, we need to solve G, right? And this is another unknown vector with given coefficients, but still E minus 1, E0, En, very similar to this unknown vector. Okay? So that is the essentially the matrix form of our system of coupled differential equation. And the purpose is to solve this one and this one, right? All the phasors, such that you can know the steady state pulse shape and the saturated gain in steady state, such that you can know the steady state pulse energy by this one. But according to linear algebra, you can roughly identify it is close to an eigenvalue problem in linear algebra, right? You have a given matrix times eigenvector equals eigenvalue, which is a number, times eigenvector itself. So this is your given matrix, eigenvector, eigenvalue, eigenvector. But it's not the standard eigenvalue problem because this vector is different from this vector, right? It's not exactly the same, this model, but close to. So now you can tell why linear algebra is so important. It's everywhere. You cannot escape the shadow of linear algebra. Even now you have been in graduate school.